All right, picture this. You're helping out a local charity, right? They're trying to set up this brand new prayer hall, and they've got a good amount of carpet, like 300 square meters worth. But there's a bit of a challenge, you see. The length of this hall, it has to be 1 meter longer than twice its width. So how in the world are they going to figure out the exact dimensions they need?
Oh, that's a pretty interesting problem, isn't it? It's like a real-life puzzle. And you know what? It actually highlights the kind of stuff we're diving deep into today, which are quadratic equations.
That's the ticket. We've been going through all these educational materials, and this whole session is dedicated to making sure you get a crystal clear understanding of these math tools, these quadratic equations. Now, I know quadratic equation, it might sound a little, technical, but honestly, it's just any equation that can be arranged in a specific way, like x to plus bx plus c equals 0, and that a there can't be 0. And the surprising thing, tons of real-world situations can be modeled using this idea.
What we want to do today is go beyond just the definition. We want to explore where these equations came from, how to spot them, and the most important part, how they can help us solve real-world problems like that prayer hall situation we talked about. We're aiming for you to walk away from this deep dive feeling like, okay, I got this. I understand this stuff,
Hmm.
and not be overwhelmed.
Sounds good to me. So first things first, what exactly is a quadratic equation? We touched on the standard form, x plus b plus c equals 0, but a can't be 0. What's that all about?
You got it. The key thing with these equations is that the highest power of that variable x there, it's got to be 2. That's what makes it a polynomial equation to the second degree. See, that's what separates it from linear equations where the highest power is 1 or cubic equations where it's 3. Different beasts.
Right, and the materials we looked at had some really good examples, like 2x plus by 300 equals ear. That's our prayer hall situation in an equation form. Then there's 2x plus 3x plus 1 equals ear, and some that don't even look like they fit at first glance, like 4 by 3x plus 2 or 1x plus 300 equals 3.
The interesting thing is, even though these look all different, they can all be rearranged to fit that standard form, that x plus bx plus c equals 0. Gives us a nice, consistent way to look at them and solve them. Take that 4 by 3x by x plus 2 equals 0, for example. That x term is sitting there in the middle, but we can just switch it around to now it's a 3x by x plus 4x plus 2 equals 0. See? Same with 1x cycle plus 300 equals 0. That becomes natix of cycle plus 0x plus 301 equals 0. Why do you think that standard form is so important?
That's a good question. I guess having everything in the same order makes it way easier to compare different quadratic equations and come up with general ways to solve them.
Exactly. It's like we all agree to speak the same language. Now remember, our prayer hall,
Yeah.
if we let x be the width in meters, and we know the length is 1 meter more than twice the width, that means the length is 2x plus 1 meters. The area, length times width, would be x times 2x plus 1, which comes out to 2x plus x. And since we know the carpet area is 300 square meters, bam, we get our quadratic equation. 2xi plus x minus 300 equals 0. Pretty neat, right?
It really shows you these equations aren't just theoretical stuff. They're connected to real problems. This feels like a modern way to think about it, though. But our materials mention the history of these equations, too. Where did this all start?
Oh, that's a fascinating part of this. Lots of folks believe the Babylonians, way back when, were among the first to tackle these kinds of problems, even though they didn't call them quadratic equations. They figured out how to find two positive numbers if you knew their sum and their product. Now, that might not sound like our x plus bx plus c equals 0, but think about it. If those two numbers add up to p and multiply to q, you could say one number is p minus x. Then multiply them, you get x times p minus x equals q. Rearrange that, and boom, x os minus px plus q equals 0. That's our quadratic equation. So even way back then, they understood the connections between the numbers in the equation and the solutions, which is pretty amazing.
That is wild, solving these without even having the fancy symbols we use today. Wow. What about Euclid? The geometry guy. How did he handle these problems?
Euclid, he was all about the visuals, the geometry. He came up with methods to find lengths that fit specific conditions. And you know what? Those conditions, they can be expressed as quadratic equations. It shows you how, even way back then, geometry and algebra were connected, like two sides of the same coin.
But it seems like ancient Indian mathematicians really went all in on the algebra side, especially when it came to finding those general solutions. We're talking about Brahmagupta, 7th century. That's a long time ago.
Yeah, Brahmagupta is a big name here. What he did was, he gave us a specific formula to solve equations that looked like x off plus bx equals c. Now, that's not exactly the standard form we use today, but it was a huge step towards a general solution. It showed a shift towards thinking about these problems in a more abstract way.
Then you have Sridharacharya a few centuries later, and he's the one who actually came up with the quadratic formula as we know it, right? Using that completing the square method.
Exactly. That method, completing the square, it's a really clever way to rewrite quadratic expressions in a form that's easier to work with. What Sridharacharya did, and later Bhaskara II talked about it too, was give us this universal tool, this formula that can unlock any quadratic equation. That's pretty powerful stuff.
And let's not forget about Al-Khwarizmi, that Arab mathematician from the 9th century. His work sounds super influential.
Absolutely. Al-Khwarizmi's work was foundational. He wrote this book, the compendious book on calculation by completion and balancing, where he laid out these systematic ways to solve quadratic equations. And guess what? He used those same techniques, completion, which is where we get the word algebra, and balancing. He even categorized different types of quadratic equations and gave us rules for solving each type.
So we've got Babylonians, Greeks, Indians, Arabs, and it even makes its way into Europe, right? With Abraham bar Hiahanasi in the 12th century.
You got it. His book, called Liber Embedorum, included all these solutions to different quadratic equations, helping spread that knowledge across Europe. It's like a big tapestry, you see, all these different cultures and time periods, all contributing to our understanding of this one fundamental concept. Pretty cool, huh?
Absolutely. Okay, so now we have a decent understanding of what quadratic equations are and where they came from. But where do they actually pop up in real life? Our sources have some interesting examples, like the one about John and Javanti and their
Oh,
marbles.
yes, that's a classic example, the kind that really shows you how a real problem can be turned into a quadratic equation. So John and Javanti, they've got a total of 45 marbles, right? And then they each lose 5. And what's left, well, if you multiply the number of marbles they each have, it comes out to 124.
So let's say John started with X marbles. That means Javanti started with 45 minus X marbles. After they each lose 5, John's got X minus 5, and Javanti's got 40 minus X. And we're told the product of what they have left is 124. So we get the equation X minus 5 times 40 minus X equals 124. Now, if you multiply all that out, you get negative XX plus 45X minus 200 equals 124, which simplifies to our quadratic equation, X minus 45X plus 324 equals 0. It's amazing how a simple word problem turns into this neat equation.
Right. It shows you the power of mathematical modeling, taking a real problem and turning it into an equation we can work with. Solve that equation, and we know how many marbles John started with.
And then there's that other example, the one with the toy makers. So there's this cottage industry, and each day the cost to make each toy, it depends on how many they're making. It's 55 rupees minus the number of toys. And on one particular day, it costs them 750 to make all the toys.
Yeah, so if they make X toys in a day, the cost per toy is 55 minus X rupees, right?
Wow.
And the total cost, well, you just multiply the number of toys by the cost per toy. That gives us X times 55 minus X equals 750. Multiply it out. 55X minus X LMS equals 750. And rearrange it a bit. XX minus 55X plus 750 equals 0. Another real-life situation that can be represented with a quadratic equation.
It really hits home that these aren't just random math problems in a textbook. They're tools for understanding the world around us. Now, sometimes you're given an equation and you got to figure out, is this actually a quadratic equation or not? How do we tell?
That's where that standard form we talked about comes in handy. You got to simplify the equation down to that x plus bx plus c equals 0 form. Our materials have some great examples of this. Like, let's take mug by 2 plus 1 plus 1 is put 2 by 3. If you just glance at it, you see a squared term and think, oh, it must be a quadratic.
And in this case, you'd be right. If you expand that by 2, it becomes x6 4x plus 4. Then add the 1, and you've got xx 4x plus 5. Set that equal to 2 by 3, move everything to one side, and you end up with xx 6x plus 8 equals 0. Fix the form perfectly right. A equals 1, b and x is 6, c equals 8.
But then you look at something like this, xx plus 1 plus 8 equals x plus 2 by 2. If you're just scanning for squared terms, you might get tricked.
That's true, because when you expand both sides, you get xx plus x plus 8 equals xx plus 4. And see what happens there. Those xx terms, they cancel each other out. Rearrange what's left, and you get x plus 12 equals 0. That's a linear equation, not quadratic, because the highest power of x is just 1. This is why simplifying is so important.
Couldn't agree more. Things aren't always what they seem at first glance. Take another one, xxx plus 3 equals x plus 1. Multiply the left side, you get 2xx plus 3x. Set that equal to xx plus 1, then move things around to get all the terms on one side. You'll have 2xxxx plus 3x minus 1 equals 0. Simplify that, and it's xx plus 3 by 1 equals 0. So yeah, this one is a quadratic equation. And just for kicks, let's look at x plus 2 equals x is 4. This one looks like it might be cubic because of that x plus 2-ish term.
True, but when you multiply out x plus 2 bellow, it becomes x plus 6xx plus 12x plus 8. Set that equal to x plus 4, and look, the exa terms cancel out again. What's left is 6x plus 12x plus 8 equals 8 equals 4, which simplifies to 6xx bell plus 12x plus 12 equals 8 equals 4. Divide everything by 6, and you've got xx plus 2x plus 2 equals a quadratic equation hiding in plain sight.
So the big takeaway here is always simplify. Don't jump to conclusions until you've got that equation in its simplest form. Only then can you be sure if it's quadratic or not.
Makes sense. So we've got the hang of identifying them. Now, what about solving these equations? That's where roots come into the picture, right?
You got it. A root or a solution of our quadratic equation x plus bx plus c equals 0 is just any value of x that makes the equation true. Plug that value in for x, and both sides of the equation are going to be equal. It's like finding the special x values where the graph of the equation, if you plotted it, would cross the x-axis. They call them zeros sometimes for that reason.
And it's important to remember that a quadratic equation can have, at most, 2 roots, no more than 2 solutions.
One way to find those roots is by factoring, something you might remember from algebra class. The idea is to rewrite that quadratic expression as a product of 2 linear expressions. So if we have something like px plus q times rx plus s equals 0, then for the whole thing to be 0, at least one of those parts in the parentheses has to be 0, right? So either px plus q equals 0 or rx plus s equals 0. That's how we find the possible values for x.
Okay, so let's look at an example. 2xx, 5x plus 3 equals 0. What we want to do here is split that middle term, that negative 5x, into 2 terms that add up to negative 5x and multiply to the product of the first and last coefficients. So 2 times 3, which is 6. In this case, negative 2x and negative 3x fit the bill perfectly.
Exactly. So we rewrite it like this. 2x equals 6 at 2 by 3x plus 3 equals 0. Then we group those terms. From the first two, we can factor out 2x, giving us 2x times by 1. From the last two, we can factor out megas 3, giving us megas 3 times by 1. Now we have 2x times by 1 minus 3 times by 1 equals 0. And look, there's a common factor there, by 1. We can factor that out, giving us 2 by 3 times by 1 equals 0.
So now, to find our roots, we make each of those parts in the parentheses equal to 0. So either 2 by 3 equals 0, which means x equals 32, or by 1 equals 0, which means x equals 1. There you go. The roots of 2x and 5x plus 3 equals 0 are 32 and 1.
Let's do another one. 6xa sectioned by 2 equals 0. We need 2 numbers that add up to minus 1, the coefficient of x, and multiply to 6 times negative 2, which is negative 12. It turns out 3 and negative 4 work perfectly.
All right, so let's rewrite it as 6x set plus 3 by 4 by 2 equals 0. Factored by grouping again, the first 2 terms give us 3x times 2x plus 1, and the last 2 give us negatives 2 times 2x plus 1. We're left with 3x times 2x plus 1 minus 2 times 2x plus 1 equals 0. Factor out that common part, 2x plus 1, and we have 3 by 2 times 2x plus 1 equals 0. Set each of those equal to 0, and we get 3 by 2 equals 0, so x plus 1 equals 0, so x plus 1 equals 12.
And we can even use factoring with equations that have square roots in them, but it can get a bit trickier. Like look at 2x was 3x plus 6 plus 0.
That one looks a bit intimidating, I gotta say. We need 2 terms that add up to negative 3 2x and multiply to 2 times 6, which is 602. It looks like those would be negative 2x and negative 2x, right?
You got it. So we rewrite it as 2x at 2 and 2 by 2x at 2 plus 6 plus 6 is 0.
Yeah.
Now let's try that grouping thing again. From the first 2 terms, we can factor out x's, which gives us 2x times by 1. Now for the last 2 terms, we want to factor out something that leads us with by 1 again. If we factor out negative 2 times, we get negative 2 times by 6 2. Simplifying that a bit gives us negative 2 times by 3 2, or negative 2 times by 322. That doesn't seem to give us a common factor of 1. This is a good example of how not all quadratic expressions factor neatly with integers or simple radicals. It's a sign that we might need something more powerful like that quadratic formula we talked about. But if someone just gave us the factors, like let's say 2 by 2 times equals 0, then we could set each part equal to 0. That would give us 2 other way to 2, so x0 is 0, so x0 is 0, so x equals 2. So our roots would be 2 and 2.
Okay, let's go back to our prayer hole problem.
2x4 plus by 300 equals 0. Our source tells us this can be factored into by 12 times 2x plus 25 equals 0. Right, so we set each of those parts equal to 0. By 12 equals 0, which means x equals 12, and 2x plus 25 equals 0, which means x equals 2 equals to t, or negative 12.5. Now remember, x is the width of a hall, a real physical thing. Can't have a negative width, right?
Exactly. We toss that negative solution out the window. We're left with x equals 12 meters for the width. The length, remember, was 2x plus 1, so that's 2 times 12 plus 1, which is 25 meters. There we go. The prayer hall should be 12 meters by 25 meters. We solved it using quadratic equations. It's pretty cool how a bit of algebra can give us real practical answers.
It really shows you that sometimes math gives you multiple answers, but you got to think about which one made sense in the real world. Not all solutions are created equal.
Okay, so factoring is great when you can easily find those factors. But what if you can't factor easily? Or maybe it can't be factored at all using, regular numbers. That's when the quadratic formula comes in handy, right?
You got it. The quadratic formula. That's our secret weapon for any quadratic equation in standard form. X source plus bx plus c equals 0. It tells us the roots are given by x equals negative b plus or minus the square root of b minus 4ak all divided by 2a. It's a mouthful, but it always works, whether we can factor or not.
And that part under the square root, b minus 4ak, that's called the discriminant. It tells us some important stuff about what kind of solutions we're going to get.
It's like a sneak peek into the answers we're going to find. Will they be nice, whole numbers? Will they be the same number twice? Or something more complicated? The discriminant gives us a clue.
Okay, so let's say that discriminant b boy k is bigger than 0. What does that tell us about the roots?
That means we're going to have two distinct real roots, two different solutions.
Yeah.
That plus or minus is sign in the formula, that's what gives us the two values, because the square root of a positive number has two possible answers, one positive and one negative.
What if the discriminant is exactly 0? What happens then?
Then things get interesting. That square root part of the formula becomes 0, so the whole thing simplifies to x equals negative b divided by 2a. This means we only get one real root, or you could say two equal real roots, sometimes called a repeated root. It's like the equation is giving us the same answer twice.
And here's the kicker. What if the discriminant is less than 0?
Now that's when we venture into some interesting territory. If b minus 4a is negative, well, we're trying to take the square root of a negative number. That doesn't really work in the world of real numbers, does it? So in that case, our quadratic equation has no real roots. It's a mind-blowing concept. Some quadratic equations, they just don't have solutions that are real numbers. Their solutions lie in a different realm, the world of complex numbers.
All right, let's put that discriminant to work with an example. Our source gives us the equation 2x 4x plus 3 equals 0. What's the discriminant for this one?
All right, so here, a equals 2, b equals negative 4, and c equals 3. Plug those into our discriminant formula, d equals b fork 8, and we get d equals negative 4 squared minus 4 times 2 times 3. That's 16 minus 24, which equals negative 8.
So negative 8, that's less than 0, which means our equation 2xx 4x plus 3 equals 0, it's got no real roots.
Exactly. Let's try a more real-world problem. How about that one with the pole in the park? There's a circular park 13 meters across, and the question is, can you put a pole on the edge of the park so that it's 7 meters farther from one gate than the other gate, and the gates are directly across from each other?
Okay, let's visualize this. We've got our circular park, right? And two gates, A and B, on opposite sides. Let's say the distance from our pole, let's call it P, to gate B is x meters. We know the pole has to be 7 meters farther from one gate, so the distance from P to gate A is x plus 7 meters. Now, since A and B are on opposite sides, the line connecting them, AB, is the diameter of the circle, which is 13 meters. And because P is on the edge of the circle, that angle APB is a right angle 90 degrees because it's an angle inside a semicircle.
So we've got this right angle triangle, APB, and we can use the Pythagorean theorem. AP squared plus PB squared equals AB squared. If we plug in our distances, we get x plus 7 squared plus x squared equals 13 squared. Expand all that, and we get x slot plus 14x plus 49 plus x slot equals 169. Simplifying that gives us 2x slot plus 14x minus 120 equals 0. If we divide everything by 2, we've got our quadratic equation, x slot plus 7x minus 60 equals 0.
To figure out if we can actually put the pole there, we got to check the discriminant of this equation. So here, A equals 1, B equals 7, and C equals negative 60. What do we get?
The discriminant D equals B4AC, so that's 7 squared minus 4 times 1 times negative 60, which is 49 plus 240, so 289. And because 289 is positive, we know our quadratic equation has two distinct real roots, meaning, yep, we can put that pole there.
Awesome. Now let's find those roots using our quadratic formula. X equals negative b plus or minus the square root of d all over 2a. Plugging in our numbers, we get x equals negative 7 plus or minus the square root of 289 divided by 2 times 1. That's negative 7 plus or minus 17 all over 2. So we've got two possible values for x. X0 equals negative 7 plus 17 divided by 2, which is 10 divided by 2, which equals 5. And x0 equals negative 7 minus 17 divided by 2, which is negative 24 divided by 2, or negative 12.
But remember, x represents a distance, so it can't be negative. We ditch that negative solution, x equals negative 12, and we're left with x equals 5 meters. That's how far the pole should be from gate B. And since it's 7 meters farther from gate A, that means it's 5 plus 7, or 12 meters from gate A. Problem solved.
One last example for the real. Let's look at 3x divided by 2x plus 13 equals 0. What's the discriminant for this one?
Okay, so for this equation, a equals 3, b equals -2, and c equals 13. Plugging those into our trusty discriminant formula, d equals -2 squared minus 4 times 3 times 13. That simplifies to 4 minus 4, which is 0.
0. So that tells us this equation has two equal real roots. One solution, but it's like it shows up twice. Let's find it. X equals -b divided by 2a, which is -2 divided by 2 times 3. That's 2 over 6, which simplifies to 13. So there you go. Our equation has a repeated root of x equals 13.
Exactly right. So to recap what we've learned, a quadratic equation has that standard form, x whole plus bx plus c equals 0. The roots, those are the values of x that make the equation true. There can be at most 2 of them. We can find those roots by factoring, if it's possible, or by using the quadratic formula, which always works. And the discriminant, that b for a c, it tells us what those roots will look like. 2 different real roots if it's positive, 2 equal real roots if it's 0, and no real roots if it's negative.
It's been quite a deep dive today. We've looked at what quadratic equations are, where they came from, how they show up in the real world, how to recognize them, how to solve them, and how that discriminant plays a key role. Hopefully everyone listening feels more confident in understanding and using these mathematical tools now.
It's pretty remarkable how this one simple concept can help solve such a wide range of problems, from those ancient puzzles to modern engineering, and even beyond that.
We've seen quadratic equations pop up in all sorts of places. Calculating areas, designing things, understanding how objects move, even in finance. It makes you wonder what other parts of our lives, things we may not even realize, are actually governed by these elegant mathematical relationships. Something to think about as we wrap up our deep dive today.